So, what we are going to be talking about today are goals and requirements. This is one of the boring ones on some level, but hear me out because I think there's still some valuable stuff I've got here. First of all, though, before we get into the specifics, there are a couple pieces of general stuff that I did want to talk about. One thing that I think I wasn't quite clear enough about last presentation was that I really do want to emphasize that I'm not an insanely technical person. A lot of the way that I'm presenting information here is the way that worked really well for me, but it's not necessarily exactly how you'll see things generally presented or line up in a textbook. I think it's a good way, and I think it's completely valid and technically correct, but I just don't want people to be under the impression that I'm giving a textbook style class on any of this and be like, oh, in the real world, people don't do it this way. That's very possible. And if there are any major issues, of course, please let me know. I don't think anything's wrong, but just want to double check because I was like, oh, someone from outside might be like, oh, this person has no idea what they're talking about. And yeah, I fully admit that sometimes that's true. Anyway, this one is probably going to be a little bit more of my personal take on something than usual. So if you're not super interested or you're like this, I wouldn't want to ever do it this way, feel free to just drop out. I wouldn't mind that at all. But again, I think there's some super valuable stuff, arguably some of the most valuable stuff of any of these presentations. And then I'm going to talk a little bit more about my goal setting and requirement process more than I am about actually applying that process, because I don't really expect that people are going to be like, oh, this is a perfect, beautiful process. I'm not going to take it and apply it in my everyday life all the time, but rather I think there's some key groundwork objects about this stuff that is worth transferring to people. Cool. So right off the bat, who cares? What's motivating this? Why do we need to talk about goals? And the number one thing is that if you're looking to build a liquid rocket engine, this is probably the point at which you will fail. And I say that just anecdotally based off of being kind of interested in why projects like this fail and looking at a lot of failures. And every single one pretty much that fails, I can have pretty easily been able to point to oh, they just didn't do some of these really basic things. And a lot of the ones that succeed, I can't do that. So hopefully there is actually some kind of correlation there. And then also because there's just not a lot of information on it. I'm not sitting here saying I'm an expert on goal setting, but I think there are basically zero resources on what setting goals and requirements for a project like this looks like. So the hope is that even if everything I say here is imperfect, it's at least something, and it's better than what perhaps exists in the broader world right now. Also worth noting, what I'm talking about here is an actual system that I thought about and applied to my engine. So it would almost feel reductive if I missed out on this part and didn't discuss it. It's probably not perfect, but I do think it's good enough for these design problems, and I do think there's some value in it, regardless of whether you personally are gonna absolutely apply it right off the bat. So, cool. First of all, what do goals do? What are they for? And colloquially, in everyday speak, these are kind of the things I would associate with goals. One, it's a nice list that organizes the things you want. It has a lot to do with what you're getting out of the project, what the end goal is, and then it drives the general process. In terms of this presentation, at least, I'm going to take issue with pretty much all of this. First of all, no, I don't think powerful goals are a helpful list. I think that's reductive to what goals can do. I would call a list that organizes priorities not a goal, but a list which organizes priorities. In my mind, if it's something you can kind of just come up with right off the bat, it's not really a super useful thing other than oh, good for organization. Powerful goals should be able to do so much more than just organize obvious stuff. And then also, I think it's slightly deeper than what you just want to get out of the project, because that implies that they're more targeted towards this end product, as opposed to something that can apply not only throughout the process, but evolve and change throughout the process. And then I also do not think it's a general driver. I think good goals should be able to make explicit, detailed design decisions about specific parts, instead of just being oh, overall, we're going to do this kind of thing. So if I don't like those kind of goals, and again, I use those kind of things all the time in everyday speak, I'm just saying in terms of the way I'm going to be using these words going forward in this presentation, in terms of effective engineering goals, I think good goals should, in short, be able to make your design decisions for you. Or you build the goals and then you can use them to make design decisions so that you don't have to, which is awesome, because for really, really complicated problems, it can sometimes be easier to build goals than it is to actually analyze things when it comes down to a complex system like this, like a rocket engine, that you probably don't understand off the bat. So to define what goals are in terms of this, I think there are two categories of goals that I'm going to propose here. One is, well, goals. And a goal sets a direction, like say speed on a spectrum of, like, say, for instance, or sorry, no. If I had something like I said, okay, the boat must go 100 miles an hour. No, sorry. If I said the boat must go fast, that's something that I would consider a goal because there's a direction, fast, on a spectrum speed. It's also something actionable that an engineer can look at and actually start to use to kind of think about as they design. And I'll go over like some examples of this. Requirements, on the other hand, are what I like incorrectly just said, something more like the boat must go over 100 miles an hour, where it sets a specific limit and it's got to be overcome. But the key like thing that builds both of these together, and I think is different from how we normally talk about goals, are that they're actionable engineering directions that you don't need to interpret too much to make decisions about parts. So a couple of brief examples. The engine shall be as cheap as possible is something I would consider a valid goal because it sets an actual direction on a reasonable spectrum. And if you told this to an engineer making a system, they could reasonably make decisions based off of it. Another one is the engine must be 1 inch long. I call this a valid requirement because it does in fact set a specific point, and an engineer could totally make an engine that's 1 inch long. Worth noting that I'm not talking about requirements that would be useful at this point, because that, I think you can imagine, would be like a pretty dumb requirement to set regardless of what your goal is, or sorry, not goal, your overarching like wants are. But I'm just talking about like what fits this kind of definition I'm proposing here. So now for a couple of examples that don't necessarily fit those definitions. Something like the engine shall provide as much learning as possible. This is like something that I think a lot of people think about and are like, oh, you know, that's pretty cool. That's something that I do want to get out of this, but I do not think that that's a valid goal because it kind of provides a direction as much as possible on a spectrum of learning, but telling an engineer that is not a useful thing to do. For instance, if I'm trying to design a data acquisition system and the person in charge says, okay, Paul, I want your focus to be learning as much as possible. I can interpret that in a million different ways. I could interpret that as I need to build the simplest one by tomorrow so that I can iterate by the end of the week. Or I could interpret that as, okay, this is going to be my like 4-year magnum opus and it's going to be the best one ever built in the world. Learning as much as possible is a very valid want, a global thing that you want to get out of the project. But to turn it into a reasonable goal, you'd have to distill it down in some way. Another invalid thing is saying that the engine must perform better than Paul's. I would call this a requirement because it's setting a bar to pass, but I wouldn't call it valid because it's an extremely broad thing across a lot of spectrums. You know, are you talking about weight? Are you talking about thrust? Are you talking about ISP? Are you talking about every single one? And if you're talking about every single one, these would probably do better as a bunch of individual goals so that an engineer designing a valve is like, okay, I know this valve needs to have more flow than Paul's rocket engine instead of just, I need a better valve, which could mean a million different things. All right, so now, given those definitions, and that's what I'm going to use going forward in this presentation, again, just in these terms to kind of like convey the information I'm trying to convey, we'll set some actual requirements for what would make these things like good or bad, not in terms of do they fit the definition, but are they productive and useful in terms of you actually being able to build an engine. Now, my first one, and arguably the most important one, if you take nothing away from this and you disagree with everything else, I would hope that you at least can identify to some extent with this, and that requirements should be unconditional. I'm also talking about goals here. Both should be unconditional. That's something that might sound really obvious. Now, what I mean by that is like, if you have a requirement, it should be a real requirement. You should actually be not okay if you don't hit it, and you should actually be okay if you do hit it. Again, seems incredibly obvious, but I find that the number one time people make these weird goals that are actually conditional and not really true is when they feel like, oh man, I don't have a goal for this. I can't think of a good goal, so I'm going to just kind of spit a number out there. And that's really, really bad. It's much worse than not having a goal at all because it shoehorns you into this kind of like arbitrary design decision that might have major impacts down the road. and you just made it because you felt uncomfortable operating without goals. In a system you don't understand, it's fine to operate without goals in some cases, as long as you understand that it's something you need to build as you gain more information, and it does eventually happen down the line. So a great example of this that I think makes it a little bit less like, oh, that's super obvious, is a goal like the engine must produce at least 25 pounds force of thrust. This is a common one I see, and I would argue that this is a pretty bad goal, as are most thrust goals. And the reason I'd argue that is because it's not a real goal. I'd say 99% of cases, if you walked up to someone with a thrust goal and said, would you feel like you succeeded if it produced 1 pound thrust less? They'd say, yeah, absolutely. Which to me indicates there's a deeper thing there. It's not really about the number to them. There's some other metric that we're still trying to dig at. So say with this 25-pound thrust example, and I asked this person, I'm like, okay, would you be okay with 24? They're like, yeah, 23, yeah, 22, yeah. And then we went down until, say, they got to 10, and they were like, no, it's got to be above 10. That's where I draw the line. I'd still probably be surprised if they wouldn't say, if I, discovered something new about this system, had some kind of caveat like, wait, but what if that extra pound costs $1,200? Then again, they'd probably be like, okay, well, I would be okay with 9 if it was really that much more expensive just for this 1 pound thrust. And the point here is, you don't know whether it costs $1,200 more for an extra pound thrust. So don't set that as your goal. Doesn't need to be set in stone. You can dig at all of these things without using numbers. Something, for example, like, okay, let's see, I have this system and I want it to be as powerful as my delivery pressure system can do, or it has to be as powerful as my test stand can withstand. In those situations, you're not locking yourself at a specific thrust level, and you're never going to put yourself in a situation where you have to make these huge sacrifices for minor improvements that you didn't care about in real life. Okay, so that's my little rant on that. I would hope that you'd agree that requirements should be unconditional. My second one is that instead of goals, you should use requirements wherever possible. And my reasoning behind that is that they are pass-fail, which makes them very, very easy for you to evaluate. That's really, really powerful in a system like this, like a tiny liquid rocket engine, because you do not know much about it, and because it is something where, because you don't know much about it, you can very easily put yourself in a situation where you're overwhelmed with information and making bad decisions. But if things were pass-fail, you'd be able to do stuff a lot easier. And it stops the need for decision matrices. Now, a quick aside on decision matrices, because I have this little opinion on it. First of all, I love decision matrices. If you're not familiar with what this is, I'm going to do one in a second. And I've done them a lot, but I think that a lot of times they cause more harm than good. And that's because they are engineering models. They are like practical engineering models when you're making your weights, when you're making your categories, in the exact same way that you would make boundary conditions in FEA. You are setting practical conditions for products to succeed. And if you're just kind of making up your weights as you go in a way that feels like it makes sense, I promise that you're setting up your decision matrix for failure. They are deceptively difficult, because if you understand if you kind of know which one you want to end up with, you're not making a real decision matrix, and that defeats the point. And I see this a lot. Like, you get numbers that don't make a ton of sense, and you're like, oh, well, I obviously didn't want to end up with this one, so let's tweak this. Well, the point of the decision matrix is to take your opinions out of it. It's to take any like emotional attachment out of it, and it's to organize everything in a very technical way. And if you're driving how you're tweaking your weights based on what you think should be the right result, well, you shouldn't have been making a decision matrix in the first place. And in cases where it truly is very complex and you don't have those opinions because you really don't know, well, then you're not getting any feedback on those weights. You sent it, and now you're like, well, I think they're good, but I don't really have any conception. And that's something really, really hard to build. So what I actually want to do is try and do an example. I'm going to share an Excel sheet and make like a very brief one. I have no idea if this is going to like actually indicate anything, but we'll see. My hope is that it will. Share, click one, Excel. All right, cool. Can you guys see my little Excel book here?
Yep.
Presumably. All right, so what I want to decide here in this example is I want to figure out what kind of engine we should build in these small little presentations. And I'm going to weigh it in a few points. And let me know if you think any of these are unreasonable. Let's see, for my categories right off the bat, things I care about. Ease of manufacture, cost, relevance to all those systems that people are currently working on, because I want the information here to like actually have to do with important stuff that's currently going on at Cal Poly. And I want it to be safe. So let's see. How am I going to weight these? How do I move? Go. There we go. Now, how am I going to weight these different things? What do I think is most important? I'm going to say ease of manufacture is my priority. I'm going to go from 1 to 5 in these. Risk, obviously we want to be safe, but some things have inherently more risk. And I'm talking about inherent risk here, not like how much our end safety goal is, but kind of how much safety work you'd have to do. That's very important to me as well. I give cost a 4 too, and relevance to develop current systems, maybe a little bit less. I hope you would not take any like major issue with these. I think they're a decent place to start. Those are my personal priorities, that's true. Okay, here's my first strategy. First strategy is don't build one at all. Second strategy, let's say, is like a small, like a model rocket. Like one of the solid fuel model rockets, like an Estes rocket. Let's say the next one is a 100-pound thrust. So still a small liquid rocket engine, but like a very weak one. And I should have like made a sheet ahead of time, whatever. And then low thrust, small liquid. So something with like very low thrust on the scale of like single digits or something. And then finally, a full-scale rocket engine. Let's just put that in there, like an actual one that could launch someone to space. Yay. All right, so that's what I want to make. We can't do that though, probably. And for ease, I'm just going to rank all of these on a scale of 0 to 3, 0 being like totally fails the metric, and 3 being 100% the best. And again, let me know if you think I'm being unfair to any of these or disagreeing. In terms of ease of manufacture, let's see. Not making one is super easy to manufacture, clearly. So is a model rocket. 100-pound thrust liquid rocket engine, that's like pretty hard to do. I'm going to give that a 1. And the kind of medium I'm going to give it to. Full-scale rocket engine, no way. That's a 0. In terms of cost, well, this is dirt cheap. This is dirt cheap too. Let's see. This is probably pretty expensive. This I'd say is in the middle. And this is also a 0. It would be insanely expensive. How close is it to our current systems? Not making one has nothing to do with our current systems. A model rocket, maybe kind of. 100-pound thrust small liquid, that's pretty much identical. And then, let's see, I don't know. Something really tiny. It uses some different manufacturing techniques than I think most people are working on here. But I'm going to, Wendy is critiquing my spreadsheet. But I'm going to give this a 2 as well. And then this, no, I give that a 2. Maybe I'm being too mean to that one. In terms of risk, super safe, super safe. This is probably pretty dangerous. This is in the medium too. Oh, look, this one ended up like all 2s. That was not intentional. And then full scale is obviously incredibly dangerous. Now, if we sum all these up, again, I have no idea if this will actually prove my point. That would be kind of funny if it did not. Put up, put up. Yeah, okay, cool. So if you take a look at this, we ended up with something that obviously doesn't agree with what we actually want to do. You guys presumably know at this point that this is what I actually want to do. This is my decision. But this decision matrix really doesn't line up with that like at all. And if I made this in real life, I'd be like, okay, let's see, like, what should I switch around? What should I change? And I could fix this in a way that would make this one win. But you don't have the luxury of doing that in a system you don't understand. And that's the key point. If I renamed these to like strategy A, and I didn't give you the information about them, like say you weren't familiar with these things, you didn't know what they meant, which is going to be true for all of the systems that you're going to be building if you actually build a liquid rocket, you would have no idea that this was something that needed to be questioned. You would just go probably with this one right off the bat. You might be a little suspicious and say, okay, it's not relevant at all, and then pick one that's at least slightly relevant. But still, we're running into issues. And what I think that's indicative of, where on earth did I put the little like zoom bar? Oh, there it is. Share. Okay, so the point here is that there are a lot of things that can go wrong. In this case, I would make the argument that if you ranked all of those, you'd notice that they ended up being ranked based off of their complexity. And that's because complexity influenced pretty much every single factor in that. So all I was really doing was ranking them off of complexity. And I can understand and see that because I really, truly, deeply understand what a model rocket is and what relevance to current systems and cost are. But in a complex system, you would have no idea, and you would not be able to find these kind of like deep, weird little factors. Okay, cool. That's my little decision matrix rant. And here's my final requirement. And that is that there is only one goal. This is another one of those weird little ones, and I don't think it's necessarily relevant to every single project you ever do in your entire life. But in the specific context of building a small liquid rocket engine, something that realistically is pretty difficult, as much as I like to say it's easy, it's very important to only have one spectrum to analyze things on. And that's because, of course, you want better everything. You always want everything to be as good as possible. That's a given. But anytime you try and optimize something, it's a trade in every single other place. And in a project like this, it sucks. It feels bad. But sometimes you have to say, I'm okay with the minimum project. I'm okay with the minimum viable product. And in fact, I'm going to try and build my minimum viable product, which always feels like in that instant, like, dang, I really wanted to build something cooler. But then you have a rocket engine and the other people don't. And then you're happy and everything's okay. So the kind of general structure we're trying to build here, again, is we have a bunch of requirements that are kind of like hurdles that we want to get over. And we take all of our options, we see which ones get over every single hurdle. And then we have one spectrum at the end that we can effectively rank those on and just pick the top rank of all of the ones that have passed. And now I'm going to kind of try and put this into practice, and hopefully that will demonstrate what I'm trying to say here, because I'm not sure how clear I'm necessarily being about what exactly the structure is here. But yeah, like I said, this is the least fun part. But in my personal experience, the amount of aggression you apply to being okay with something lamer than you expected you'd be okay with is directly proportional to the likelihood that you're going to succeed in a project like this. And that's why these goals are powerful. If you just ended up with goals that are like, I want everything to be as good as it could be, you're not going to meet that. It's not going to help you make decisions. But if you really dig deep and are like, dang, this sucks, but I guess if I think about it, I would be okay with this, you're setting yourself up for success because you're making sacrifices early on and you're not having to go back and make those sacrifices way down the line when you realize your design's impossible. So let's actually do it. Here is my strategy. If I had to define it, I think there are 5 steps, and we're going to go through them for this actual little rocket that we're going to be designing here. First is to list those overall wants, those things that in the context of this kind of presentation, I'm not going to call goals, but are things that you kind of want to get out of it, but wouldn't consider as valid engineering direction. Then we're going to turn them into those valid requirements. And again, I'm saying requirements specifically because we want as many requirements as possible. We're going to take these ones and we're going to try and translate them into requirements, into specific bars that we want to overcome. And we're going to at the end of the day, ultimately find some that we can't do that with and are like, well, there's no really good requirement that fits there. We're going to set those aside. We're not going to force requirements. And then we're going to take those ones that we made and we're going to step them down. We're going to say, okay, this is what I thought right off the bat for the requirement. Would I be okay with a little less? Well, I guess maybe. Would I be okay with a little less? Yeah, I guess maybe. Would you be okay with a little less than that? And there's a point where you'll say, no, I actually wouldn't. I'd feel like I failed. And then you go just a little bit up and you set your goals there. And again, that's the unpleasant part, but that's the part that works. So then you take the set of requirements you've made and you look for kind of loopholes. You're like, all right, so have I really fully defined the system? You know, is there a system I can imagine that would fulfill all these requirements, but still not be what I want? And then you can use those loopholes you found to generate new requirements that you didn't think of. Now you kind of go through this loop again and again and again until you can't think of any loopholes and you've got these ones kind of left over where you couldn't set requirements for them. And then you can take those and start translating them into the goals because again, we want to minimize the number of goals. So I think it's going to be a lot clearer if I actually apply it to something. And let's do that. And what I'm going to apply it to is, again, the thing we're going to be doing here. I'm going to be doing that with a list of overall wants first, because that is the first step. The overall wants that I want out of this, and I sat down, I think about it. This isn't just an example. These are actually true. This is an actual process that I followed in terms of like how I want to do these presentations. 1, I want people to learn about rockets. 2, I want people to think rockets are easy. And 3, I want people to build rockets. Those are my only priorities here. And I want everything, I'm going to do everything in my power to make all of those happen. So now let's take these wants and start turning them into hard requirements. What requirements for the actual rocket engine do I have that will make people learn about rockets? And well, honestly, I don't think I have any, because I think as long as people think they're easy and are building them, I think they'll inherently learn about them. So I don't really need any particular requirements for this. And this is an interesting point because the strategy doesn't just take your wants and then translate them into specific things. Sometimes it makes you realize, oh, this thing I thought was a goal is achieved by all my other stuff. I don't even need it. It can make the system simpler instead of making it more complicated. 2, I want people to think rockets are easy. And I guess the 2 requirements that I drive from that are 1, I want it to be designable in these sessions alone. You can tell that that is a bar that you could pass, and that's a direction you could give to an engineer. You could say, hey, you're designing this valve and you need to design it in a way that it is done in X number of minutes. And then I want it buildable by someone with a yellow tag. That's something that I think is personally required for me to feel okay with this. I think about that. I think, would I be okay if it required blue tag? Probably not. And then in terms of for people to build rockets, honestly, I also think it'll be handled fine by the other ones. Cool. So we've built these 2 requirements. Now let's go to the next step, which again is to reduce them. So I'm going to look at this requirement. I'm going to say, would I be okay with less? And I actually, with this specific requirement, I changed the way I was going to do these presentations, which is I thought, would I be okay if it was designed in these sessions except for the calculations? And I was like, no, I think the calculations should be done here. I'd feel like it wouldn't be real if I didn't do the calculations. Then I was like, okay, but would I be fine if it was designed in these sessions except for the CAD, and the CAD could get done outside and maybe I'd record a video? And I was like, well, I don't want to do that, but I guess I wouldn't feel like I failed. And I was like, darn, well, now I can't be a hypocrite. I need to turn that into the requirement. So the new requirement is this, the minimum that I'm okay with. Any less, and I would feel like I failed. Any more, and I would feel like I succeeded. That means it's a good requirement. Number 2 we're going to look at is the other one, buildable by someone with the yellow tag. So the question is, would I be okay if 1 or 2 parts were blue tag parts? And honestly, the answer is no. I would feel like I had not succeeded in this endeavor. So therefore, we're going to keep that one the same. That is a legitimate hard limit. Cool. Now, next step is to brainstorm unacceptable solutions. What kind of rocket can I think of that would be designable minus CAD in these sessions and buildable by someone with the yellow tag, but I would still be like, oh, no, that's not what I want to do. And here are a couple things. First thing that's right off the bat is if these were true, but it was insanely expensive, that would suck. So I do need some kind of requirement there in terms of price but I can't think of a specific price where I'd say $1 less than I'd fail, $1 more than I'm happy. So we're going to leave that one to the side for now, but keep track of it. All right, what else? Well, something that is nothing like an actual liquid rocket. You know, if it like was valid in these two cases, but was a solid rocket, I'd be like, oh, well, what was my point? And what I'm going to start with in terms of that requirement is to say the subsystems of this thing that we're building have to be the same as my presentations. And again, it's worth noting that I'm skipping through a couple steps here, but my first thought here was actually like, okay, the subsystems need to be the same as the subsystems in rockets people are currently building at Cal Poly. And then I was like, no, that's a bad requirement because that's too general. You can't tell that to an engineer. They don't know which rocket, they don't know which systems. And so I specified it and I limited it down to just my presentations. Cool. So now let's see, are there any other things that would be unacceptable? And I think about that and I'm like, well, yeah, if it performed terribly, if it just like wasn't like, if it was super lame, I would be upset. And my first reaction to that is to say, okay, it needs to have 50-pound force thrust. So now what we do is we go back. We put those in the requirements and I start analyzing them. The same subsystems as my presentations. Can I reduce this anymore? No, I'm happy with this. I have no further tolerance for it being any less. 50 pounds thrust. Well, again, this is the example. Would I be happy with 49? Yeah. 48? Yeah. And I was thinking about this and I went down to like 5 and I was like, well, I'd be happy with 5. Would I be happy with 1? I mean, that would mean it like wasn't really working right, I feel like. And then I realized there was a deeper thing I was trying to get at, and it wasn't an actual thrust goal. It was something else that quote unquote makes it real. And in my mind, that in this case has nothing to do with thrust. What I think it has to do is hitting Mach 1 at the throat, which you guys might not know, but is a key characteristic of a converging diverging nozzle. Now, this is a really good example where if you were setting these goals and you didn't happen to be aware that Mach 1 at the throat was a key characteristic of a converging diverging nozzle, it would make sense to leave it at the side and say, I can't set this goal yet. I don't know enough. Or alternatively, to go do research and figure out, okay, I want it to be real. What does it actually mean for it to be real, quote unquote? I also do want to make a brief note that there are exceptions to all of these. And like an interesting fact is for my rocket engine that I built and fired, I did actually have a thrust goal, despite everything I'm saying here. And at first it kind of annoyed me. I had a 10-pound thrust goal and I was like, darn, I'm really kind of just like throwing my system aside. But then I thought about it more and I was like, well, would I be fine with 9 pounds of thrust? And the more I thought about it, I was like, no. And it's not because of some deeper engineering thing. It's because in my like human brain, I personally don't think I would be able to be happy if I made single digit thrust. I really do believe that if my rocket had made 4 pounds of thrust, I wouldn't have gone home being like, I built a liquid rocket engine. I would have been like, oh, that thing wasn't a real engine. So it's totally irrational. It's totally human. And there's some times where you can break these rules, but as long as you're truly happy with nothing less, or yeah, you're truly happy with nothing less at all. Anyways, let's move on again to brainstorming the unacceptable solutions. Now I can think of a lot less, but one I have thought of, say, the second time around is, well, if it blew up and killed everyone, but all of these were true, I would be unhappy. Or I'd be dead because it blew up and killed me. But I would not, well, people wouldn't be happy. It wouldn't achieve the goal of everybody learning about liquid rocket engines because they'd have lots of holes. And so what I'm going to set as a limit there is safe enough to fire in either propulsion lab. I thought about that a little bit, and that's something that I felt like, okay, that's a decent enough bar. So let's add that to our goals. Oh, and also, again, I still have this something extremely expensive loophole here that I still can't think of a good goal for. And the situation, by the way, was not contrived. This is actually how I thought through all this. Anyway, I'm going to add that to my requirements. And I'm going to skip it for now, but then I go and I'd be like, okay, am I okay with a little bit less? Am I okay with a little bit less? In this case, I'd say, no, I'm not okay with a little bit less. This is like the bare minimum I need to be happy. Awesome. Now we have our requirements. Now we get that one goal, okay? Everything here were the ones where we forced ourselves and went through pain to set specific bars. Now we get to have that easy one where it's like, I want this direction on this spectrum. And it just so happens, and I find that this is true a lot of the time, which is the nice thing, is that there was one thing lying around, and that was that something extremely expensive. So super easy, worked out great in this case. I'm just going to turn that into my one goal. And I'm going to say as inexpensive as possible. There's a direction, cheap, on a spectrum, price. And now we have it. This might seem like not that far removed from just writing down what you want, but these are some seriously powerful things. And I think hopefully I'm going to be able to demonstrate that more as we continue through these presentations and as I apply them to literally everything from valves to pipes, and as hopefully we can expand and change them. But for now, let's see. Let's actually go and use this to make the same decision that I kind of tried to demonstrate that a decision matrix wasn't perfect for. Again, this is not like me curating this. I legitimately think, or my hope is, again, and again, this might not work, but I hope you still believe that like the system is somewhat reasonable and you get the idea. Who knows? Let's give it a shot. Let's see what happens if we apply this goal strategy to the problem we had before. And I'm going to do that. Did I quit out of? I did, didn't I? Oh, no, I didn't. Nice. Where did it? Wait, can you guys still see the Excel? Oh, wait, no, never mind. I just didn't click a button. There you go. Can you guys see the Excel sheet now again?
Yep, you're good.
Okay, cool. Also, Adam, if you said something, I can't hear you. I don't know if anyone's saying anything. I think maybe I just can't hear anyone. So hopefully I haven't been interrupting everyone. Everybody's been asking questions. I've just been, that would be funny. Okay, so now we're going to go and we're going to take this and we're going to do things a little bit differently. I shouldn't have renamed these like strategy. Oh, I can just do that. Okay, cool. So now let's go down here, and instead of weights, we're going to type in the requirements we just set. Designable minus CAD in sessions. That's one. Yellow. Another one is manufacturable by Yellowtech. Same. And I'm going to write cost there as a spectrum, not as inexpensive as possible, because I'm going to evaluate cost in the same way that I evaluated cost when I was making the decision matrix. Okay. Now in terms of weight, I guess I could put this as 1 and everything else is like, I don't know how I want to go about that. And now, because this is a requirement, I can just do yes or no. So designable minus CAD in all of the sessions. Could I do that if I didn't make one? Yes, I could design nothing as fast as I wanted. Okay, and to keep people happy, I don't know why I can't. Why can't I do? Oh, there we go. I will do conditional formatting. So if it's no, it will be red, and if it's yes, it'll be green. Won't that be beautiful? Okay, cool. Could I design a model rocket minus CAD in these sessions? Yeah, absolutely. Could I design a 100-pound thrust small liquid? Honestly, you know what? I'm going to say yeah. I'm going to give myself the benefit of the doubt. Could I design a small liquid? Yes, I believe that I could. Full scale one, not a chance. So notice we could stop here with the full scale. It's eliminated. Bam, it's gone. Not a chance we can do it. But anyway, let's move on to the next one. Could I do nothing with the yellow tag? Yeah. Could I make a model rocket with the yellow tag? Yeah. Can I make this with the yellow tag? Again, I'm going to be generous. I'm trying as hard as I can not to shoehorn the one that I want to get out of this into my goals. I'm going to say, you know what? I think you could do it. I think you could do it. Yes, you could obviously do this. This is still a big no. Does it have the same subsystems as my presentations? Obviously not. Obviously not. Yes. Yes. And again, I'm going to give full scale the benefit of the doubt and say yes again. Is it going to reach Mach 1 at the throat? Nothing is obviously not going to do that. Model rocket, I'm not sure. I don't, you could, it depends on what you did. I'm going to say no in this case though, because it's really not typical. This could definitely reach that, and a small one I think could reach that too. So could this. Could you build one that's safe to fire in our prop lab? Nothing would be safe to fire in the prop lab. So would a model rocket, and so would these two. The full scale one would definitely not. So worth noting already, we're down to 2. Everything else has been eliminated. And now we can use our one goal and rank them. Which one's first place in terms of cost? Well, obviously the smaller one is going to be cheaper than the bigger one. So this one gets first place. This one gets second place. And this one is the one that we built. We're not going to build this one because it doesn't have the same subsystems we're Mach 1 at the throat. This one has the same issues. This one lost on cost. This one didn't lose in cost. And this one is bad for obvious reasons. So look at that. It works out. That's super nice. And I do understand that this is like a somewhat contrived situation where it's like, I kind of get how things are going to go, but the hope is that you can see here, you know, if you questioned me on this, if you said for any of these decisions, justify it, I could give you a justification. I could tell you why this doesn't have the same subsystems as my presentations. I could say why this is safe to fire in the prop lab, and I wouldn't need much information about these systems to tell that. I feel like I could probably, and hopefully you could, determine all of these yes or no's by either searching on Google or asking around about what's been done before at Cal Poly or how much things cost. None of this takes technical experience or ability to build these systems to do. Now, if we compare that to the decision matrix, if I presented this at a PBR and someone said, okay, so why is ease of manufacture exactly 1 higher than cost? The answer is, well, because that's what I want. And that's not a particularly strong answer. What it implies is that these could get tweaked. You know, if I made it like this instead, would you really take issue with that? You wouldn't really have any way to. Whereas if I went and I changed any of these, I said, yes, I could design a full-scale liquid in CAD and these sections alone, you would say, no, you're a liar. That's not true at all. And that's the other cool thing. Another person can look at this and really easily be able to evaluate whether what you're doing makes sense or it does not. And then, yeah, that's pretty much all I wanted to get through in terms of that. The hope is that you'll believe me even more as I use this in other systems that are a little bit more general. Okay, back to the little presentation. But yeah. No, that's not the presentation. That's a presentation. So yeah, that's it. This is pretty much everything I wanted to talk to in terms of that. The hope is that this at least drives you somewhat to think a little bit more intentionally about the goals you set in the context of a project like this. And cool. Glad you guys sat through this. Hopefully the people who are watching or not virtually, everyone's virtual, but the people who are watching on YouTube will sit through it as well. And next week, we're going to move on to, shocker, some actual real life rocket things, specifically talking about propellants. But at least for now, that's everything I can think of. So thanks for showing up.